several different topics that have been changing over the years. And one of these is that troubling backward rotation of Venus. All the planets rotate about the sun in the same direction, but Venus is unusual that it rotates sort of backwards compared to what Earth and Mars do. And another topic is sunspot groups and AI enlightenment. And what sort of time scales, how long have we actually known that Venus rotates a little backwards? And
Hey,
well,
Fred,
what's today?
are you
It's
sharing a PowerPoint slide?
it's showing on the screen here.
Yes.
No idea.
I see a screen. It just says a different point of view. Troubling back.
Yes.
This is Chris. I do see it.
Yeah,
Okay,
I
share
see
here.
that screen too.
Okay, great. Keep going.
And so, this is actually Earth Day. And how many here were alive when this picture was taken? Sort of showing your age.
Yes.
Picture of Earth taken from the moon. And one of the things, in terms of changing, one of the things they're talking about, Earth is showing more and more blue as ice melts. And notice the water absorbs more energy than ice. And so it's sort of a runaway effect. Once that ice starts melting, you get more water, you get more heat absorption. And
Awesome.
just thinking of things differently, like what would our sun look like viewed from Alpha Centauri? Have you ever thought about that? Hmm. Hmm. We disconnect my mouse, so oh, and some of those topics and published papers on some of these different areas. And so one of those is in terms of Venus, and another is in terms of some motion of the Jovian planets. This one in Jovian planets just came out last month, about maybe 30 days ago. And the third, maybe time scaling of evolution of terrestrial planets, which we will not get to today. And speaking of backwards Venus, the whole idea of how we started getting some of this knowledge and exploration is when a Soviet general came to a Soviet scientist and asked, we're developing a very large ballistic missile. No, correction. we're developing a very large rocket. Where should we send it to impress the world with the might of the Soviet Union? And
He likes it there.
and so
He likes new things.
Tony, put it to.
so the
Everybody
science
needs to mute.
whether we can mute the home ones.
Let's see. You're still good, Fred. I muted those people.
And so that Soviet scientists thought, well, I would never gotten funding for such things if I had requested it. But he thought, Venus is twice as close to Earth as Mars ever is. Venus is right next door to us. Venus is only about 5% smaller than the Earth. And initially, the thought was that Venus should be like Earth twins. Sort of assuming for the moment that Venus, named after the goddess of love, always wore a veil of modesty. Have you ever seen a clear day on Venus? No. And so the gist of that, once they started to go to Venus, they found out that it was totally different than initial expectations. And one troubling thing was that since there's never a clear day on Venus, the only way they got a hold of it as rotating at all was by using radar. So if you bounce radar signals off, you get an idea of rotation. And as both Mars and Earth have about 24-hour days. It was very unusual that Venus, from the radar, actually seemed to be rotating a little backwards. And if you raise your right hand, you can sort of get an idea of that and have your fingers going around for the rotation on this axis. Then if you swing your arm about, you can see, say, Earth going around the sun. But now with Venus, if you hold your finger up and rotate backwards, and then rotate your arm around in the same way, and try that. It's very difficult. It just doesn't seem to jive.
Yeah.
So those brave enough to try that. And so there's some mysteries and sort of a new thing on the block, just sort of available more or less in the last couple of years, is the idea of using artificial intelligence. And sort of three general things they see with artificial intelligence. One is you can see how results fit sort of standard models. And well, the standard model is my editorializing magnetic braking as some versus some weird collision. And the use of data generation and calculations, and one of the things now is using artificial intelligence. You can just ask, where were all the planets on such a date? And AI can spit out that answer without much calculations or so. where just a few years ago, you had to either the idea of looking things up or calculating. And you can do a literature search very easy. You just ask it, can some similar results be found elsewhere? And seemed to the answer they got no for magnetic braking. So maybe the results will be unusual, and no for the Jovian planet influence. And sort of a fourth thing, so the idea that you find after time, artificial intelligence seems to gather all this information, and occasionally then it starts spitting out things that items 1 through 3 are more retrieval of information. But when we get down to general intelligence, it seems like AI says, you've given me all this knowledge, and then at some points it wants to say, well, let me say this about that. Stupid humans are limited. And the prevalent model found out that some sort of giant impact, and it was just right to leave Venus spinning slightly backwards. And I would say this is a very weird collision that left no evidence. Venus doesn't have any rings, it doesn't have any moons. And solar system formation, like a low mass star, can take in the order of about 30 million years. And the question was, there's just one short-lived collision, or, do we depend on some sort of collision effect that normally something short compared to a human lifetime? Maybe there's other things. And our solar system is rather unusual in terms of what we see in exoplanets now, that our system has a large friendly Jupiter that keeps these Jovian planets well separated from the terrestrial ones. And so we do see and can deduce things from very far back in the future that we might not be able to determine if we had a Jupiter that was more erratic or such. And in our system, these Jovian and terrestrial planets are very well separated. And it's sort of like AI speaking. So Fred Cadieu's explanation for Venus backward spin, Cadieu argues that Venus retrograde rotation is a natural consequence of its interaction with the sun's magnetic field. And that would occur in the early solar system when the sun's field was much stronger. And key points from this model, electromagnetic interactions can act over long timescales, unlike collision effects that are, they may last, few years or weeks or years, but nothing in terms of timescales of the Earth. Yes.
The polar axis is upside down, right? That's why it's rotating backwards.
Well, that's what one way of describing.
The polar axis.
Well, that's just describing that it's getting backwards. You're just saying it's spinning backwards. You say it's turned around from Earth. And the solar magnetic drag, as the sun's magnetic field swept across Venus' electrically conducting core, it induced currents that exerted torques that gradually reversing its spin. And one thing, it also induced a model sort of parameter in terms of average density that works out that if something has a density greater than a certain amount, then it's a magnetic and can have such things as plate tectonics, has some mechanisms for long-term energy dissipation. And so at formation, that sun's magnetic field is strong, so it interacts with that electrically conducting, but not non-magnetic core of Venus. And so if you have the sun rotating around, dragging that magnetic field, Venus is going to try to back up. It tries to avoid that flux entrance. And that's a very key thing. And so AI recognizes there's no need for collisions. Unlike mainstream models that invoke giant impacts or tidal effects, Cadieu's theory relies purely on electromagnetic interactions. And that sun's early strength, and there's micrometeorites so they can age from going way back, in which they can see magnetic fields induced in those. And so it's evidence that that field was once fairly strong. And that magnetic braking stops the rotation, so the dynamo stops. And one key thing is that interaction is independent of the sun's magnetic polarity. So our star, like many stars, is changing the direction of its magnetism currently about every 11 years, probably a different rate in the distant past or so. And is that going to disrupt the motion? And it's not an obvious question. And AI can be opinionated. One thing it comes out with that Cadieu's work offers a compelling electromagnetic alternative, conventional impact-based explanations. And let's see a little more how that comes about. That if we have our solar system, and there's 4 terrestrial planets here, like Mercury, Venus, and initially it seemed like there was 2 planets near the same orbit. And a planet, to be justified as a planet, has to operate to clear that orbital distance. And it seemingly did that by the impactor, or what's left over. Earth acquired a lot of the heavy materials and radioactive materials and things more like a truck interacting with a car. Earth got by far the best of this interaction, and it split apart into a moon of much lower density, and an Earth actually elevated to an average density greater than Mercury. And we have things above this red line. Venus being below, Venus core is electrically conducting, but not magnetic. And there's sort of a working hypothesis that Mars is probably lower conductivity. Earth is now shifted. So Earth is magnetic and can manifest plate tectonics. Earth can survive long periods where Venus, the only way to dissipate large amounts of energy that are still initially present is to sort of burp. And so Venus periodically remakes the surface, which is bad news for evolution. Hard to get things going on Venus. And just a little review of electromagnetism. So we all know that opposite magnetic poles attract, similar magnetic poles repel. And so we probably had little Scotty dog magnets as kids, at least the older ones. But now, little magnets have become so powerful that you don't want to give those to a child, because he can hold them apart and they go whop. And so, I've spent many days in the lab making different magnetic films. And modern magnets are not toys. And nothing, currents and motions in electric conductors act to oppose magnetic flux changes. And it's sort of equivalent to saying that electrically conducting system interacted with a magnetic system is magnetic pole independent. And that's a key thing, that such forces, irregardless of how the spin is changing from 11-year cycle to, it takes 22 years to come back, such forces can act over millions of years versus short time scales for collisions. And so I can have a fairly weak force, but if that acts over a very long time period, it can certainly be more effective than some, maybe some miraculous collision could just do things. And so we can make a little model and representing a core of Venus as being electrically conducting, and have some magnets that can be swing around. So they're swinging around like this direction, Venus, to avoid the flux, is going to want to back up. And that flux don't try to come near me. And once it has a flux, it wants to keep it. And here we have a model of Venus and Venus core, and the brass disc represents the electrically conducting core of Venus, and note that it's non-magnetic. Well, it want to be playing it, and the arms the volume is fairly low. How the magnetic field from the sun, as the sun rotates, would be dragged across Venus. And notice that magnetic fields come in two polarities, where we can either have the magnetic field going down into the disk or coming up. And you can easily verify that if I bring a little magnet up to one side, see it's attracted there.
I get it. Can't fool me.
It's repelled on the other side. Let's try that once more. So that's repulsion. And then that's attracting. And so we want the response to be in terms of the electrical conductivity and not the magnetic properties of Venus, since Venus is non-magnetic. And notice that, rather amazingly, a low-mass star of the sun is generally said to take about 30 million years to form. So it's amazing we wind up with an object of where the sun's polarity seems to flip or interchange on the average about every 11 years. And so we don't want the effects to be magnetic polarity dependent. Otherwise, we would have a rather confusing state. And so in this case, we want the magnetic field to be dragged across the disk. And by Lenz's law, the disk is going to try to respond to oppose the change in flux. And so if the magnetic field is rotating about in this direction, then the disk is going to try to rotate to oppose that change. And so in this case, the magnets are attached to a little fan mechanism so we can drag the field in. And then we do have the desired effect, where the disk rotates because of the entry. And notice that the magnetic field is entering, and afterwards those here connects opposite polarities. So it's really dependent on just the electrical conductivity and not that there's any magnetic response from Venus. And notice if we stop that, and say if I start the disk rotating opposite to magnetic, we'll see if it can self-reverse itself.
Wow.
It knows what it needs to do to obey Lenz's law.
And once more,
Yes.
Without any magnets. Just airflow would cause the same effect though.
Wouldn't cause the
the
reverse.
disk is
Yes, it would.
really acting in its motion to oppose the entry of that flux.
Yes, which would cause this to spin.
And so Venus, even though it's rotating around the sun
Yes, this model, yes.
in, say, this direction,
Yeah, but
Venus itself is rotating sort of oppositely from what you might expect.
like it needs to make a model in which the magnetic poles were eliminated.
So Fred, this is dependent on the assumption that Venus has a conductive core, but not its own magnetic field.
Right.
Can you explain the idea of a conductive core but not magnetic? I'm not sure why,
Just
how that,
in this case, like iron's a darn good conductor. A star has a lot of hot iron. They can act as a conductor, and Curie point of iron is, not much over, the order of 1,000 degrees. The sun is certainly core regions far hotter than that. It's not going to be magnetic because of, iron's a magnetic material. It can still conduct electricity, but it's not going to generate or manifest a magnetic field.
oh, okay. Thank you.
Well, you need a more ordered state. Electrons are still moving if you heat it up above the Curie point.
And Fred, am I right that Mars also doesn't have a significant magnetic field of its own?
Right.
But it's not subject to this effect because of the density difference or the distance difference?
Well, the density, and also it is less metallic, so it has a lower conductivity, so it wouldn't be as sensitive to this effect.
Fred, you mentioned that the magnetic field of the sun is a lot greater beyond the solar system. I assume it's got less of an effect now. Is this retrograde, or is this effect still causing Venus or influencing Venus to have that reverse, rotation, or is Venus still rotating in retrograde manner just out of inertia?
I get out of it inertia.
Yeah. Fred, am I correct that Venus's slow spin is currently slowing down?
Well, we've only been measuring things for 50 years.
But radar is pretty good. I thought that the consensus was that it's slowing down slightly.
I don't
Am I correct on that? Okay.
I don't think it's certainly been measured. And we want to look on a separate effect, looking at that low mass star in terms of a paper that was published last month. We bring together sort of tubules of magnetic flux and start building a star, sort of crude. We have sort of what's called poloidal fields, which are more fields that we're measuring out away from the star. But because of differential rotations, we start to get fields going around called toroidal field.
That circle representing the radius of the star, or the diameter of the star.
Yes. And so in this view, these tubules inside the star reflect more out to the surface. In a little more professional drawing, we see these magnetic field lines that then become, you see, more concentrated near the polar regions. And so with the star rotating, it's going to be the polar regions that rotate slower compared to these more equatorial type regions. And so as the star rotates, we get these toroidal fields.
Right? Yeah, that's what happens after so many rotations. The magnetic field get all twisted. That caused the eruption of the sun surface and developed the sunspot.
Yes, it's happening near the surface.
Yeah, that's why it's all twisted and they get erupted.
And it's only more recently that people are starting to more consider it's more a near the surface interaction rather than with the core of the sun or the core of a star. The temperatures are just such that it's not going to maintain a magnetism there. And so these swirling, collapsing tubulars, and it can take about 30 million years to get a low mass star forming. And the magnetic field more resides near the surface. And that magnetic braking is, just as a slower rotation, be near the poles. And when toroidal field high, we're more likely to get a breaking of the surface or a sunspot. And so surface granulation or some areas introduce a large noise factor. And hemispheres are more likely to be asymmetric. We're not going to get a uniform response, and we'll see how that comes in. Magnetic field oscillates sort of between toroidal and poloidal fields. So as that field reverses, the energy is going more from poloidal, say, up to toroidal going around to poloidal pointing down. And so the complete reverse cycle takes about 22 years rather than just the 11 years. And what I'd say, this maximum toroidal field is related to the motion of the Jovian planets. We'll see how that comes in. So in our solar system, we have 4 terrestrial planets fairly close in, and this is not to scale. It's normally hard to make a diagram that shows both, but it's the distance out to Jupiter is 5 times greater than the distance out to Earth. And so, you know, planet more about halfway out in our solar system is actually Uranus. And we have 4 Jovian planets much farther out. And so if we start looking at that in terms of our sun, where would a balance point be if I were to put Jupiter and the sun? And the thing that's not readily recognized, that if I do the sun and Jupiter, that balance point actually comes a little outside the surface of the sun, which means there's a big sloshing factor as things go around. And so we do that for the different planets. We can then get a center of mass distance from the sun divided by the sun radius. And we can see that Jupiter is a little outside, Saturn about halfway. And these Jovian planets still substantial. It might look like these are nominally 0, but if we use a semi-logarithmic scale, you can actually see there's about 3 orders of magnitude between the coefficients for terrestrial and Jovian planets. So if you're summing things over, these are not going to add very much compared to, the effect of the Jovian planets. And so we want to make an equation then, we call it Z, where we use these coefficients and then the angle for, say, Jupiter, Saturn, Uranus, and Neptune. And the sum is over each planet, but only the Jovian ones are really going to be of much consequence. And so that Z of t is just the projected distance from the sun center to the center of mass. And then we just need to evaluate that over time. And there are certain apps, or now you can just use AI. But if we have these going around and have Jupiter at a certain angle, Uranus and Saturn and Neptune, in this particular case, if we take this and view it from some, say, distant star over here, we can see how these would sum, and we use the cosine, and we're measuring angles from saying 0 to 180 degrees to 270 to 360. So we can do a summation over time for these different positions. And if we then plot that distance, you start to recognize that, gee, this has a extremal value at just the time positions where we have maximum sunspots. And this is just plotted from 1900 to 2040. but those orbits have been well defined over much longer periods of time. You can run this back or you can run it forward. And so when we have this flux near the surface, we're going to have flux breaking out of the surface is when we get a sunspot. And like before, we didn't see a sunspot when these fields become twisted, and we're more likely to get a sunspot when the toroidal field is large. When we have more poloidal fields, we're not going to have much twist. So we're not going to have a sunspot forming. So we look at a butterfly type, which then sums things over northern and southern hemispheres. Notice, when you look at this in detail, you can see the pattern, say in the north and the south, are not correlated. They're more or less independent. So sometimes you would get a spot up here, sometimes a different location downstairs. And normally, you're just taking these sunspot diagrams, have just sum the sunspots over the entire surface. So a butterfly diagram attempts a more spatial relationship in terms of the sun. And so this, more recent periods or sunspot cycles, just summing over those, instead of butterfly, it's just adding them up, top and bottom. And here's a diagram for cycles from 22 to 25. And try to line these up so these, and you can see where cycle 22 is right here, cycle 23 right here, cycle 24 right here, cycle 25 right here. So you can extend this into the past or the future. And so that enhanced toroidal field is necessary for sunspots, but it's not a sufficient condition. It needs some sort of noise, such as surface granulation. And the asymmetry of the butterfly diagrams is due to such noise type factors. This is sort of AI speaking. And these papers make two key assertions: that Jovian motion modulates the timing of the toroidal magnetic field maximum. And he argues that combined motion of the four gas giants shift the solar system barycenter in an about 11-year rhythm, which in turn modulates when the sun's toroidal field strengthens. So there have been many attempts trying to get a match to just using Jupiter alone, but that's not a good fit. There you would expect more a 12-year cycle, but combining the different Jovian planets then gives you this much more, I'd say, agreement with experiment. And the sunspot groups appear because the toroidal field is strong, but with stochastic noise. And Cadieu explicitly states that sunspots emergence is not deterministic. Even during a toroidal field maximum, the number of grouping and sunspots depend on stochastic processes in the near surface regions. So in Cadieu's own framing, Jovian forces set the timing of the active window, but not the detailed grouping pattern. And so it's just sunspots, and say currently we're still in the tail end of cycle 25 that peaked in about December of 24. And cycle 26 should peak in, say, March of 2037.
Should everybody sell their solar scopes?
Yeah, Fred?
Yes.
Fortunately, yeah, now the peak was like late 2024. They predicted it's going to be a secondary maximum, but unfortunately, it didn't happen. Now, the main numbers is heading down, so it's not officially yet. The next number is 2024. It's not officially yet. Still have another year or two, but preliminary results, it seems like if there's going to be no secondary peak like other cycles. So it's a little unusual, but now it's heading down to the minimum period, which should occur around 2030, 31 years.
To get such behavior, you would expect to have that Z function be modulated in some way. For our particular grouping of Jovian planets seems to give a very smooth Z function. If I change a Jovian planet, make a Jovian planet much closer to the sun, I remove that as a main sort of jostler, but I then produce much more potential for a modulated Z function. And so if I look at an exoplanet system, that would have a large high mass planet in closer, then at certain spacings would I get a smooth function or a much more modulated. And you can sort of see that in terms of, well, the second paper is published, about 4 weeks ago now. And it might show, it's a different thing, but if I change position of Jupiter with Venus, and then Saturn becomes more dominant farther out, but I get a system with much more modulated behavior. Certain patterns would probably give a secondary rises or such. Our system does not seem to behave in just that way. And so we don't see this secondary system. I would say that's expected. If I was to see it, I would have some sort of a more modulation pattern. Well, I say this is a different paper from a year ago where where all of these terrestrial planets started all covered with salt water. And then the planets had to evolve to have surfaces above the water where it could start to get fresh water forming. But that's a different topic. And so I think it would, end at this point.
Be what would be the cause of the double peaks in the sunspot maximum?
Well, you're expecting a fair amount of noise. So you're expecting there to be a lot of stochastic noise that's not going to repeat necessarily from one cycle to another. So that noise is a sort of a necessary part to really get a sunspot. And so that Z function tells me sort of a window in which I can get sunspots, but it doesn't tell me which exact spots are going to be involved. So it have an inherent noise factor to me. Maybe in 50 years, you could figure out more details. I don't think it's going to show up. So we do have a model you can come try that's going to behave similar to what we saw in the.
Do you need electric for that? Because I can bring my cord over and
Well, we arranged the cord in advance.
oh.
So it really does work in real life. And notice that the swinging around one cycle that would correspond to about 22 years. And so it can take more than 10 cycles that they're really going. So the effective time dependence is easily be a much longer time scale than a human life. If I have, at least 10 reversals before it really gets happy with the motion.
There's still, are there still theories for Venus's rotation based on tidal interactions, or has that been largely dismissed?
No, I say the prevailing model, for lack of a bigger effect, has some impact. But that impact left no evidence that it ever occurred.
The reason I asked about the tidal thing is that would be a longer term rather than a single.
Tidal forces can't torque up, okay? Tidal forces converge to lock. So the only viable theories of impact, which let's finish up because I just want to make comment if I could.
Yeah.
Been a long time, blown my mind, and you did it twice. Right.
So, yeah. So I thank you for that because these days it's very difficult to get my mind going. You made two very important points, all of which makes total sense. I don't know the details, but I thought I knew all this stuff, and obviously not. So there is the idea that you can have a magnetic torquing effect is certainly to be looked at, and your Z function is remarkable. I had never heard of a Z function. I was an astronomy professor for a long time. I never heard of a Z function, but it's incredibly correlated, which immediately makes you say, "Hey, you got to look at this." So, Fred, I thank you very much for blowing my mind twice. Thank you.
It's generally it's not easy to change the mind of these older scientists.
I get it. I know there's eddy currents, yeah. But that model, just for someone who hasn't done the drop the magnet in a continent, and then the magnet slows down as it falls. Yeah. That was really good, Fred. Yeah.
Good.
Right, up there, the fourth down, to say correlation between the rotation and what? Something missing there, what?
Can't tell you the artificial intelligence.